The universe is vast, unimaginably vast. Within this cosmic ocean, our solar system is but a tiny island. For centuries, we humans have looked up at the stars and wondered, are we alone? This question, perhaps the most profound we can ask, continues to drive our exploration of the cosmos. We build incredible machines, telescopes that act as our extended eyes to peer into the deep unknown. Recently, one such marvel, the James Webb Space Telescope, turned its gaze towards a world far, far away. This distant planet, known as K218b, has captured our imagination. It has become a focal point in our relentless search for life beyond Earth, a place where answers might just be waiting. K218b isn't just any exoplanet, it's special. Located 124 light-years away in the constellation Leo, it orbits a red dwarf star. Think about that distance. A light-year is the distance light travels in a year, nearly 6 trillion miles. So, the light we see from K218b today started its journey when great thinkers on Earth were only beginning to map our own world. What makes K218b particularly interesting is its classification as a Hycean planet. This means it's thought to have a hydrogen-rich atmosphere and, crucially, a vast ocean covering its surface. Liquid water, as we know it, is a key ingredient for life. This makes K218b a prime candidate in our cosmic detective story. The initial observations of this intriguing world sent ripples of excitement through the scientific community and beyond. Imagine a planet significantly larger than Earth, about 2.6 times its size and 8.6 times its mass, potentially harboring conditions suitable for life. The possibility, however remote, that we might find something there is electrifying. It taps into our deepest sense of wonder, our innate curiosity about our place in the grand cosmic scheme. The announcement of potential findings from K218b therefore was met with bated breath. Could this be it? Could this be the moment we discover we are not the only thinking beings in this immense universe? The James Webb Space Telescope, or JWS, is our current champion in this quest. Its powerful instruments can analyze the light passing through an exoplanet's atmosphere. As starlight filters through, different molecules absorb specific wavelengths of light, leaving a unique chemical fingerprint. By studying these fingerprints, scientists can deduce what an exoplanet's atmosphere is made of. It's like cosmic forensics, piecing together clues from light years away. The data gathered from K218b was eagerly anticipated, holding the potential to either confirm our hopes or send us back to the drawing board, reminding us of the universe's capacity for surprise and complexity. The search for life is a marathon, not a sprint, and every clue is vital. In April of 2025, a team of astronomers, led by the insightful Niku Madhusudan from Cambridge University, made a startling announcement. Using the keen observational capabilities of the JWST, they had detected something very interesting in the atmosphere of K218b. Among other gases, they found traces of dimethyl sulfide, often abbreviated as DMS. Now, why would a molecule like DMS cause such a stir? On our home planet Earth, DMS is overwhelmingly produced by life. Think of vast blooms of marine phytoplankton in our oceans. They release this gas. Its presence in the atmosphere of a distant world immediately raised eyebrows and quickened heartbeats. The detection of DMS was not a fleeting glimpse. The Cambridge team reported that their finding reached a 3 sigma statistical significance. In scientific terms, this means there's only a 0.3% chance that the detection was a random fluke, a mere ghost in the data. Alongside DMS, the telescope also picked up signs of methane and carbon dioxide, common gases, but their presence in conjunction with DMS added to the intrigue. However, Professor Madhusudan and his colleagues were careful. They urged caution, emphasizing that this was not a definitive discovery of life. Science demands rigor, and one set of observations, however compelling, is just the beginning of a very long and careful investigation. Dimethyl sulfide is considered a potential biosignature, a chemical indicator of life. Its strong association with biological processes on Earth makes it a tantalizing molecule to find elsewhere. If K218b truly is a Hycean world with a global ocean, then perhaps, just perhaps, something akin to Earth's marine life could be churning out DMS there too. The researchers also hinted at the possible presence of dimethyl disulfide, DMDS, another sulfur compound that can be linked to biological activity. The initial report, published in prestigious journals, sparked a wave of discussion and further research. It was a moment where the abstract question, "Are we alone?" felt a little less abstract. The excitement was palpable. Headlines around the world buzzed with the news. But within the scientific community, excitement is always tempered with a healthy dose of skepticism. That is the nature of the scientific method. A discovery, especially one as profound as potential evidence of alien life, must withstand intense scrutiny. The data must be reanalyzed, the methods questioned, and alternative explanations explored. The detection of DMS on K218b was not an endpoint, but rather the firing of a starting gun for a new phase of intense scientific inquiry, a process designed to ensure that when we do make a claim, it is built on the most solid foundation possible. The initial thrill surrounding the K218b findings soon met the rigorous and sometimes sobering process of scientific verification. Science thrives on challenge, on independent teams testing and retesting claims. In May 2025, not long after the initial announcement, other research groups began to publish their own analyses of the JWST data. Luis Wellbanks from Arizona State University and Matthew Nixon from Maryland University, interestingly both former students of Niku Madhusudan, presented a reanalysis. They employed different statistical models and expanded the range of possible chemicals they searched for in K218b's atmosphere, from Madhusudan's initial 20 to around 90. Their conclusion was stark: the claims for potential biosignatures vanish. This counter-argument suggested that when you look for a wider array of chemical compounds, the specific signal attributed to DMS might actually be explained by other, more common, non-biological molecules. Another team, this one from the University of Chicago, and led by postdoctoral researcher Raphael Luque, reached a similar conclusion. They re-examined the JWS data, focusing on its inherent noisiness. Space telescope data, especially from such distant targets, is rarely crystal clear. Luque's team argued that the data was simply too noisy to confidently support the presence of DMS. Their paper submitted to proposed that other molecules such as ethane, a common hydrocarbon not indicative of life, could produce similar spectral features to those observed. The Chicago team, which included Michael Zhang, pointed out a crucial aspect of atmospheric spectroscopy. Many different compounds, especially those containing a carbon atom bonded to 3 hydrogen atoms, a methyl group which is part of DMS and ethane, can absorb light in similar ways. Disentangling these signals requires exceptionally clean data and very careful analysis. Furthermore, they highlighted that when data from multiple observation passes by, both the Webb and Hubble telescopes were combined, the evidence for dimethyl sulfide actually weakened. Adding to the chorus of skepticism, a separate paper led by Oxford astrophysicist Jake Taylor also reported finding no strong statistical evidence for either DMS or its cousin, DMDS. This unfolding debate is not a sign of failure but a testament to the strength of the scientific process. It's how we inch closer to the truth. Niku Madhusudan, to his credit, welcomed the scientific discussion. His team even released another preprint, expanding their own chemical search list to a staggering 650 compounds. This newer study reportedly still found DMS but not DMDS, and intriguingly suggested the presence of other compounds like diethyl sulfide and the toxic methyl acrylonitrile. However, Luis Wellbanks voiced concern over the rapid evolution of Madhusudan's analysis without new observational data or models, highlighting the complexities and potential pitfalls in interpreting these faint cosmic signals. The quest for certainty continues. The initial wave of excitement over K218b has now settled into a more measured, cautious optimism. The subsequent analyses from various independent teams have underscored the immense challenges in definitively identifying biosignatures on distant exoplanets. Raphael Luque and others emphasize that the current JWS data, while groundbreaking in many ways, is still much too noisy for a slam-dunk confirmation of something as specific and life-indicating as DMS. In science, when faced with ambiguous data, the principle of Occam's razor often applies. The simplest explanation is usually preferred. If a spectral signature could be explained by a common, non-biological molecule like ethane, that interpretation often takes precedence over a more extraordinary claim, like alien-produced DMS. Professor Madhusudan, however, remains confident in his team's ongoing work and anticipates that more data, expected over the next year from further JWST observations, will help clarify the situation. It's also important to remember, as he and others have pointed out, that even if DMS is unequivocally confirmed in K218b's atmosphere, it doesn't automatically mean life. While on Earth it's predominantly biological, DMS has been found on lifeless celestial bodies like asteroids, suggesting non-biological pathways for its formation might exist elsewhere in the universe. This complexity means the scientific community must remain vigilant, constantly questioning assumptions and seeking multiple lines of evidence before making any definitive pronouncements about extraterrestrial life. The entire K2-18b saga beautifully illustrates the critical importance of rigorous scientific methods, including robust data collection, multiple independent observations, cautious interpretation, and thorough peer review. Discovering life beyond Earth would be one of the most profound achievements in human history. Such a monumental claim requires monumental evidence. We must be patient, persistent, and meticulously careful. The universe doesn't give up its secrets easily, and the search for life is a painstaking process of eliminating uncertainties and building a solid case, brick by evidentiary brick. This ongoing debate is science doing its job, refining our understanding and our methods. Looking ahead, the quest to understand exoplanet atmospheres and search for biosignatures will only intensify. Future missions such as the European Space Agency's Ariel, Atmospheric Remote Sensing Infrared Exoplanet Large Survey mission, are specifically designed to characterize the atmospheres of a large and diverse sample of exoplanets. Each new observation, each debate, and each refinement of our techniques brings us a step closer. The discoveries and discussions surrounding K2-18b, regardless of the final verdict on its DMS, are invaluable. They sharpen our tools, hone our instincts, and fuel our enduring fascination with the cosmos and the possibility that somewhere out there, we are not alone. The search continues.